Right, we're recording. So the theme is how do you get agents from like low-level physics, and the goal is to just like walk through the whole damn stack.
Yeah.
We'll start basically at the bottom and move up from there, and you just ask questions anytime you got anything that like seems fishy, seems confusing, you're curious about.
Okay.
All right, so first things first, what are we starting from? What do we mean by like low-level physics, right? So basic starting point is going to be, we've got a world that has two key things going on. First, locality. Second, symmetry. What do those mean? So locality first. Important property of physics in our world is it's local in the sense that like things only directly interact with things that are nearby in space-time, right? So you've got this idea of a light cone. You've got sort of an event at this particular point in space, a particular point in time. It can only directly interact with things right nearby it, and then to interact with things further away, signals have to like propagate through space-time, right? And this is something that like we can check experimentally, of course. We can check that like things only interact at a distance or over time via some intermediate interactions by like measuring and controlling those intermediate reactions, right?
Okay.
This is what science does. We like carve out a little subsystem of the world, and then we like control for stuff going in through the boundaries of that little chunk of space-time. And we see that like the same thing goes on the inside if you control for what's happening on the boundaries of it.
Okay.
That's locality in a nutshell. Make sense?
Yeah, I'm thinking if there are any counterexamples.
Mm-hmm.
So like, sometimes you impact, like, an object can have impacts on a field, but even those propagate, like, I think, like, there are gravity waves,
Mm-hmm.
which suggest that even gravity propagates at the speed of light for less than the speed of light.
Yep.
Yeah, are there any nearby you might think it's a counterexample?
So the place where we would start getting into things that could look more like counterexamples would be once we get higher level than just the lowest level of physics.
Okay.
We're going to get to that. Like, pretty
Yeah, I guess there is logical decision theory-ish stuff, which is...
yeah.
I don't know if that's what you're thinking of. Okay, but yeah, locality makes sense.
Cool. Then second piece that goes with this is symmetry.
Yeah.
Like science wouldn't work if we couldn't like carve off little subsystems of the world and then be able to carve off some other little subsystem at a different point in space and time and say like, these two are basically the same, or like they're doing the same thing, or they're governed by the same laws, right?
Okay.
That's symmetry. We're able to like identify, for instance, that the laws of physics are the same at all the different points in space and time. That's identifying a symmetry.
I don't have. Is there a way that you can be confident that that is true about our actual universe? It seems like, you go far enough away and you're like, oh, the constants have changed.
Yeah, so two things there. First, we cannot be confident that the symmetry will hold like through all time and space, right? Like,
Yeah.
It's always possible in principle that there's some point where like once you go past here, the laws of physics are just totally different, and we just haven't gotten there, right?
Yeah.
So we don't necessarily know how far the symmetry extends. We can say that like the symmetries we have discovered do like exist, because otherwise we wouldn't be able to predict things at all. Like they exist at least within the region around us that we've explored.
Yeah, okay, but so symmetry is just that if you have the same inputs into a subsystem, you get the same outputs, leaving aside that it's like tracking that your initial conditions are exactly the same is not really tractable.
Yeah, so like wording it in terms of inputs and outputs is already like putting a little more structure in there, but that's the basic idea.
Okay.
Okay.
Great.
Any more questions
I
there?
don't think so.
Cool. So those two pieces are sort of our foundational building blocks. We're assuming that our low-level universe has a lot of symmetry to it and locality to it. The sort of language that's natural for talking about a universe that has both symmetry and locality is several ways of framing it, but circuits with symmetry, base nets with symmetry, Turing computability, all of these are sort of gesturing at the same thing.
What does it mean for a base net to have symmetry? That it's the same. Yeah. If you draw your box, it doesn't seem like it is true if you drew a base net and you took boxes out of it, and you're like the properties of this substructure of the base net is the same as this other substructure of the base net. They would have, different weights, different.
So let me give you an example.
Yeah.
Imagine I've got. So I could start with a relatively simple base net that looks like, say, this, right? But now what I'm going to do is tile the thing. So I draw a box around this little block, and I'm like, okay, I'm put a copy of it here, a copy of it there, and this thing's going to keep going. And we could imagine it keeps going in the other direction, or we could imagine that just ends there, either way.
Okay.
This would be a base net with symmetry. I've got like copies of the same block repeated as like subsystems of my net.
Yep.
Make sense? And this is sort of the bare minimum model that gives you both locality and symmetry. The locality is captured by, like, for every little piece of the system, it only directly interacts with its immediate neighbors in this like graphical model.
Yep. Although, given that it is a graph, it's not even clear what it would mean for it to not to interact with something that isn't. It's in, like, you draw an arrow
Exactly.
between any two things, and they're now immediate neighbors.
Exactly. That's like that's why I say this is sort of the bare minimum model for talking about symmetry and locality, is because a graph is sort of the bare minimum model for talking about locality.
Yeah.
It's just like directly representing which things are directly connected to which other things, and then the paths in the graph capture like indirect interactions.
Okay, but symmetry is not necessary. Locality is like sort of baked into a base net.
Mhm.
Symmetry, there's a subset of the space of all the base nets.
That are
some of which-
symmetric.
Yeah.
Or subsets of them could be symmetric. Like
Yeah.
we could have something like this, but then upstream of it, there's a different part that's just like doing a completely different thing that then feeds into this symmetric part.
Right.
Yeah.
Okay. You said base nets, Turing machine, something else.
Yeah. So these end up being basically equivalent. Circuits with symmetry was the other one.
Okay.
You can view a program, like a Python program, for instance, as representing this sort of structure.
Yep.
So the example I use here is, here's a factorial program. Factorial then is going to return n times factorial of n minus 1. A base case that I stick in here, that's 0, then return 1. Let's do that. So a messy way to write that, but
Okay.
Now I can write this as a circuit with symmetry, or a base net with symmetry, by unpacking this part and then tiling it. Here's how that works. So I've got my factorial function. It's going to take in an n, so that comes in right here, and it's going to spit out some result. What do I do with the n? Well, I check whether n is equal to 0. If it is, then I just directly return 1. If it's not, then I'm going to return a different thing, which is n, we're using n now, n times the result of another factorial function. Okay, and then I'm going to have n minus 1 right here. That's passing into my other factorial function. So this is going to be my little symmetric block.
Okay. Which we're calling recursively.
Yeah, and that recursive call corresponds to symmetry, similar to what we had over here.
Okay.
Continue on down that way.
Although in this case, the arrows are in a maze net. The arrows are like probability flows. I'm not even sure what I would call them.
You can view them the same way in both of these. This is actually a well-defined base net. The only thing that's unusual about it is that every single one of the nodes is deterministic. So the probability distribution just has like all of its weight on one outcome.
Okay. All right. Okay, so every computer program is a base net.
Or it represents a base net.
Yeah, although a degenerate base net where every transition function is 1.
Yes, unless you're using like random number generation, in which case it would
Yeah, okay.
So that's the basic idea, is we observe that like our universe has this thing going on with locality and symmetry, and sort of a natural bare minimal model that captures those things is Bayes-Nash symmetry or Turing machines or programs or what have you.
Okay.
So that's going to be the like lowest level thing that we want to build on top of. So that makes sense as a starting point?
Yeah.
Cool. Does it make sense how like if you knew the laws of physics reasonably well, you could represent them sort of in this way?
I mean, so one thing you can do is you can talk about like the nodes in your base net can be a giant state space of all the atoms in a universe.
Not quite. That wouldn't be one node. That would be like you would have a whole bunch of nodes spread out that would each represent state at a little point in space. That's important because it has to capture locality.
Well, I'm imagining you have like a giant like exponentially just a giant space of giant dimensional space, and then you have a point which is the state of the universe given an atom here, an atom here, an atom here, and then there's a dot that can.
So the thing that would be a state of the universe would be a cut across one of these graphs. So like for instance here, if I do a cut through here, that's the
Okay, so there's a dimension for the state of every particle?
Yes. So, well, if you're thinking of it in terms of particles, yes.
Okay, what should I think about it in terms of instead?
Well, like you think about it in terms of fields, in terms of particles, whatever. The important point, like what's special about a particle is that a particle is at a particular point in space-time. Or at every time it's at a particular point in space, so it's local.
Okay.
Whereas if you're thinking about like the joint state of a whole bunch of particles, that would be taking information from a bunch of different points in space at a certain time.
But there's more information about an electron than just its location.
Correct.
And even its location is not a scalar.
Correct.
Because there are 3 dimensions in space.
Correct.
So it can't be the case that each node is just one particle. Each particle
state.
And we're just like assigning a code whereby if it is in the top half of the universe, that's a 0, and if it's in the bottom half of the universe, that's a 1. And then we just have like a long binary code that represents all of the states of each of the particles. Is that the sort of thing that I should be thinking of?
That's the right flavor of thing, yeah.
Okay.
You need a little more information in the state than that, like you said, but that's the...
Yeah, you need the location, you need the, like, I'm an electron and not a proton. I guess you need to describe what those mean.
Yep.
And then...
You need, like, states and momenta, and that's all that shit.
Yeah.
I should also highlight here that, like, this is already... Like, we're already simplifying from the actual laws of physics a bit here. Like, we're not talking, like, if we're drawing these things as graphs, then we're sort of discretizing things to some extent. We're not accounting for, like, rotational symmetry of the universe. Those are things where, like, if you do some fancy limit shit with these graphs, you can account for them, but they're not going to be particularly relevant to the phenomena that we're going to be thinking about. So,
okay.
Just be aware that we're already making some simplifications.
Okay. I think this is okay. I may come back and be like, wait a second, how does this?
Yeah, that's fine.
This sort of graph actually work?
Mm-hmm.
But okay, we're gonna represent stuff about each of the particles or each of the fields or what have you and as you play things forward in time, there's like propagation of effects from this particle bumps into this particle, and it bounces off, and then both their locations change and both their momentums change.
Yep.
And that's the universe is just a bunch of
Bunch of that.
Yeah.
Yep.
Big puzzle graph of things affecting things.
Yep. Perfect.
All right.
All right. Let me check my notes. What's next? All right. Two important things that we don't yet have in this picture. First, we don't necessarily have a favored ontology for local states. Here's what that means. If we imagine some like alien scientists coming along and studying the same universe, we do have good reason to expect that like they would discover the symmetries, they would discover the locality structure, so they get like sort of a similar graph. Why? First of all, the symmetries, these are like predictable structure, right? These are the things where like you see the thing over here, you're going to see same thing over there. That's predictable structure. That's a thing that is like instrumentally useful for prediction. Make sense?
Yeah.
Similarly with locality, carving off little local chunk of the universe, that's something where there appears to be a sort of underlying local structure of like things only interact with things nearby in space-time, and that seems to be a sort of property of the universe separate from the like our particular way of describing it. Yes. What that doesn't necessarily give us is a particular way of representing the state of this node. So for instance, let's imagine like very simple case, let's imagine the universe of this factorial function.
Okay.
So this node is like a number, right? An integer. In the universe of this factorial function, we could figure out the locality structure. We can see which things are interacting with which other things.
Yep.
We can see the symmetry. But that doesn't nail down choice of representation of that number. So like alien scientists might want to represent numbers in a different way. In our computers, we'd be representing them as like a sequence of bits, right? With a particular kind of encoding.
Yep.
Even in our systems, some systems will use little endian encoding, some will use big endian encoding. So these things are like represented this way or that way, conceptually.
Yep.
In more bizarre systems, you could imagine people use other kinds of number systems. Maybe they use like gray numbers or something wacky like that. Or maybe they just like keep everything encrypted at every stage. The point is, as we like go through later stuff, I want to like assume that the locality structure and the symmetry are sort of universal things that we would expect like even alien minds to figure out. So insofar as we're building our concepts up from locality and symmetry, we should expect our concepts, the like concepts that we're using at a higher level, to also generalize. But we don't want to rely too much on particular representations of individual nodes. We want what we're doing to be sort of invariant to that.
So particular representations, basically we could be using different codes
Mm-hmm.
to encode the same information.
Exactly.
Now, there is some, like if I'm using base 2 or using base 8,
Mhm.
there's still some fundamental similarity between what I'm representing. Like I can translate between
You
them.
can translate between them.
Is that all that we mean here?
Yep.
Are there other? So there's base 2, there's base 8.
Mhm.
I guess you can also have like arbitrary codes that don't have any obvious
Like,
structure.
Yeah, base aren't like our standard encoding methods at all.
Yeah.
Yeah.
Where you just like have a list of bits.
Mhm.
And
Or even bits. Maybe they're trits.
yeah.
Maybe they're continuous voltages. I don't know.
Okay. Yeah. So there's different ways to represent the nodes.
Mhm.
There. Ultimately, we can translate between any
Yeah.
encoding.
And as we're like going through this story, we want to, so similar to how like physicists will try to build theories of physics that are invariant to coordinate shifts,
Okay.
we want to be telling a story here which is invariant to different ways of encoding the individual notes.
Okay.
Make sense?
Yeah. Is there a reason why that's important to you?
So part of what we're trying to do here is like build a story of how you get from low-level physics to agents in a way that would like generalize or universalize.
Yeah.
Say like it's going to make sense for a broad range of minds to view these sorts of things as agents, or to view like the sorts of things we've been talking about in a similar way to how we've been talking about them.
Okay.
Does that make sense? So we want to tell like a sort of universalizable story.
Okay. Fair enough.
All right. Check my notes. I think we're now done with the low-level part. So I'm going to erase this, then we're going to start.
You maybe want to take a picture first?
Yeah, that's a good idea. Also, we'll break the video here. Do this.